Hello, I will talk about how I see the future of ZK engineering will be, and I will describe a landscape which currently Powder is a great example of, so you will find some overlap between my talk and the previous talk. So a bit about myself, I started playing with ZK snarks in IDEN 3 with CIRCOM. Later on I joined PSC, and I've been working on developing the ZK VM with Halo 2, so I spent a lot of time writing circuits. And through this experience, I've thought a lot about the high complexity of the circuits that we write. And also, I'm personally worried about soundness bugs that we have in the circuits because of the massive complexity they have, and also because it's a very different model than traditional programming. So I will start describing two kinds of categories of programs that we want to verify on ZK snarks, and this will be used later to explain how this future landscape I think will look like. Actually, I want to say that this is half prediction, but also it's an observation of a trend. So I think many people will agree on how this future will look like. So the first category is static computation. So you can imagine this as a program that has minimal control flow. So you could imagine that you write the program, and every time you run it, it takes the exact same path. This would be not Turing complete. It would be highly structured. And some examples of this would be field arithmetic, signature verification, hashing, machine learning, and so on. And then the other category would be general computation, where there is control flow, so you can do branching, you can do loops. This is Turing complete, which means that you can do the same. It's a superset of static computation. Everything you can do with static computation, you can do it with general computation. And just for some examples, this could be credential rules checking, email parsing, processing how blockchain transitions from one state to the next, some game logic. And now, as a description of how we currently approach writing circuits for ZK snarks, whenever we find logic that doesn't have control flow, it's usually easy or straightforward to write the circuits because there is an easy mapping to the arithmetization. But every time we find control flow, this becomes, on one hand, difficult because arithmetic constraints are very static, but you want to write code that can take different paths. So every time you have some ifs or even nested ifs, the arithmetization of that becomes quite complicated to follow. And if you have loops where you don't know the maximum number of iterations you will take, doing this in arithmetization in the naive way is quite painful, but also it's efficient. So here I made some diagram where you could imagine a program that has some test for a condition, and depending on the condition, you take path Y or Z, where Y is bigger than Z. So if you imagine when you execute this program on a CPU, you will pay for the number of steps of execution. So if you take path Y, the cost will be higher because there are more steps, but if you go to path Z, it's just a few steps. But then when you turn this into arithmetization, actually you are creating a proof. And when you design the circuit, you don't know which path is going to be taken. So no matter if you take path Z or Y, you are paying the same. And usually it's either or the worst case path or even the sum of both paths. So now I think about the kind of applications that ZK developers write. And my claim is that when a developer wants to create a ZK application, most of the logic is going to be in the general computation side, at least the logic that particularly identifies this application. And maybe there may be some static computation that can be identified into particular blocks. And the point is that general computation can easily be verified with ZK VM, so that is a circuit that verifies the execution of a Turing-complete virtual machine. And then all the logic of this application will be written in a traditional program, compiled into instructions of this virtual machine, and then verified on this circuit that just verifies the trace of execution. And also there's a note that if there are some specific parts of static computation, you could have a specific circuit customly designed for that part. So the point of having a generic ZK VM for any application has really good benefits. So on one side, the ZK developer doesn't need to write circuits. They just write a traditional program that is compiled into this instruction set. And this is very good because there is less training for developers, and also writing regular programs. It's something that we have been done for many years, and developers will be more familiar with this. And plus, there is less opportunities to create soundness issues, because as long as all the program is just instructions, for instance, there's not going to be under constraints. There still can be some under constraints and some conditions, but this is minimized a lot. So the point is that we only need a ZK VM to build any ZK app. And in this scenario, you only need one-time effort to write the circuit that verifies this trace of execution of the virtual machine. And now reviewing and auditing ZK applications is highly simplified. But of course, going from a custom written circuit to a ZK VM will have some performance overhead. So my claim is that most of the time, you can identify the blocks of static computation of your applications, and instead of running those with your instruction set of your VM, you would have some kind of coprocessors that have custom circuits implemented to verify those static computations. And even I would say that these specific blocks of static computation will be common among many ZK applications. So the regular developer will not need to write these circuits. It would be similar to if you want to write a Rust program and you want to do Keccak hashing, you don't write the code for doing the hashing. You usually reuse it from some implementation. So here's an example of how imagine things would go. And I mean, I've had in the ZKVM project, we have been developing the Patricia Merkle tree circuit, and it's taking a long time, and it's a very complex thing because the Patricia Merkle tree takes a lot of different branchings and have a lot of edge cases, which means these either loops or ifs that are hard to translate into circuits. So I would imagine you would have a regular program that verifies a Merkle-Patricia tree. And then every time you need to do a Keccak hash, you would use this coprocessor that in the circuit side has a specific circuit to verify Keccaks. And now let's see how this could translate to performance. So these are just made up numbers. I don't know if you can see them well. So let's say that the MPT circuit is on the cost is 90% hashing and 10% is the rest of the logic. And we have an VM that will have an overhead of a custom circuit, and let's say that it has perhaps 10x overhead. So this approach gives you that 90% which was hashing, it's still at 90% because you are doing it with custom specific circuits. And the 10% that is the rest, you multiply it by this 10 overhead. So at the end, even though the VM had 10x overhead, you only get 2x overhead, but a lot of benefits because you don't need to write custom circuit for all the logic. So I think this is a big improvement. So what kind of landscape do we get from this? We have that regular ZK app developer will not be writing circuits anymore. They will just write traditional programs that will be compiled into an instruction set that is verified by a circuit. Ideally, this instruction set will be an existing one, and the reason for that is that you get all the benefit of of being able to use existing libraries. Like in Powder Risk, you just take normal Rust code, you can use any Keccak library and you compile it, or any, I don't know, parsing libraries, whatever you need, and you just compile it to RISC and verify it on the circuit. Then I imagine there will be a small group of experts writing the ZKVM circuits, as well as the static circuits to be used as extensions or coprocessors. And this means that on the landscape of ZK languages, which is something that I've thought a lot about, I think in the future there is no need for an easy to learn ZK circuit language, because there's not gonna be new developers who are not familiar with ZK that will need to write circuits. Only experts will be writing these circuits, and this will be a non-frequent task. And you can imagine this, I think it would be similar, like, I don't know, if you nowadays want to write a program that does AES encryption, probably you are going to use a library that has some of the AES implementation written in assembly, and it's calling some extension of the CPU that does some of the AES encryption for you. And this is in assembly, so it's hard to write, but someone who was expert wrote that. Perhaps there's even it's been formally verified because it's write once and used in many situations. So there are some challenges of this approach, and one I can think of is running these proofs on mobile, but I thought of possible solutions to even realize this feature in mobile. So for instance, we see that proving systems are improving performance constantly, so maybe one day we will be able to run this on a phone. Also, with this approach of having static computation moved to specific circuits, it means that only we need a few cycles for the main logic. So maybe a phone will be able to handle this because it's not like millions of cycles of the CPU being verified, being proven on a phone. Perhaps instead of targeting an existing instruction set, we can use ZK-friendly VM, which would be lighter on the proving side. Or perhaps if we cannot solve this via any of the first options, we can imagine like shared computation between a phone which deals with private inputs and then delegates the rest of the computation of the proof to a server. And perhaps there are other challenges, and I would like to hear what other people think. So this is not something that is not new. There are other projects that are already doing this. So for instance, RISC-0 is doing SNARK to verify RISC-V execution, and they have this idea of accelerators to run hashing. Polygon ZKVM is built on a circuit that verifies a custom instruction set. So since this is a custom instruction set, they have to write their code in assembly instead of a program that compiles to this assembly. And they also have external circuits to accelerate computation. And actually, I wrote here VMs without acceleration, but I just learned that Powder does coprocessors. But we have Cairo VM, which is a custom instruction set and a circuit. Jolt is a RISC-V circuit that verifies instructions with lookups. And Powder, we've seen it before. And probably there are more. This is not an exhaustive list. And that's the end of my talk. So if you have any question, I'll be happy to answer.
Thank you very much, Edu. I think we have time for 1 or 2 questions, depending on how quick is the first one. So anyone wants to jump in? Okay.
If you use the, let's say if you constrain at the RISC-V level, does that mean you also rely on the compiler to, you kind of believe the compiler can generate the correct bytecode?
Yes, but I think that's the assumption we already make in traditional computing, so I think it's safe. But I would even add to that, so this is an interesting question, but the point is that we have a lot of tools to analyze traditional programs. Probably if you come from Rust, there's a lot of people looking at the Rust compiler implementation, so you get the benefit of all this previous work.
We have time for one more short question. Okay, then thank you very much, Edo, for your talk.